Okay, I'll get started with today's class. Today's class continues on from Tuesday's class on the topic of relativity, Einstein's relativity. On Tuesday's class, we talked about the space and time landscape or space and time fabric in relativity. In today's class, we're going to move on towards talking about energy and momentum in relativity. So on this little slide here, I've listed the items that I want to work through. The first one I want to look at is velocities in relativity. And specifically, I want to talk about relative velocities and adding velocities, and ultimately the fact that in relativity, there's a speed limit on how fast you can go. You can't go faster than the speed of light. In classical space-time, there's no speed limit on how fast you could go. You can go infinitely fast in classical space-time. I then want to move on to say a few words about the laws of motion and the action of forces in relativity compared to relativistic physics compared to classical physics, or relativistic mechanics compared to classical mechanics. And then that'll lead us into this topic here, which is to discuss relativistic energy and relativistic momentum. And we'll look at a few examples of relativistic energy and relativistic momentum. Okay, this slide is just to summarize last class because it's really the basis for this class. In last class, we introduced the foundations, the postulates of relativity. And if you remember, one of them is that the laws of physics are the same in all frames of reference, like a frame of reference on a platform or a frame of reference on a train. And the second one was that the speed of light is the same, identical in all frames of reference, like the frame of reference of a platform or the frame of reference of a train. So that was the foundations, the cornerstones of relativity. And then we discussed two consequences of those foundations. One was this notion that the time between events is not the same in different reference frames. So if different observers watch a clock from different reference frames, they measure different time intervals for the ticking of the clock, for the passing of 1 second on that clock, or the passing on of 1 hour on that clock, depending on their motion. And we met this equation for that. The effect was called time dilation. And this was the relationship between the so-called dilated time and the so-called proper time when observers view a stationary or a moving clock. The other big consequence that we met in the last class was that the length of objects was also observer dependent. So if you observe a meter stick or some other object in different frames of reference that are moving with respect to one another, then the different observers in the different frames of reference will disagree on the measured length of that object. And that effect was called Lorentz, was called length contraction. And it was described by this little formula here. And these are the two key ways in which space and time is kind of distorted. They're stretched or compressed in relativity compared to classical space-time, where everybody agrees on the time between events and everybody agrees on the distance between events. In these equations, if you remember, gamma is the Lorentz factor. And gamma depended on your motion with respect to the meter stick, if you're measuring its length, or with respect to the clock, if you're measuring time intervals with the clock. And specifically, that equation was this little one here, where V is your motion with respect to the stationary clock or the stationary meter stick, and C is the speed of light that everybody agrees on. Okay, so now let's talk about relative velocities, adding velocities, and the speed limit C, how that appears, how that comes about. So let's take a look at this slide. This slide and the next slide are kind of partners. And these two slides are partners because they describe how to add together velocities in what we call Galilean space-time. That's the sort of classical space-time in Newton. And what we call Lorentzian space-time. That's the space-time of Einstein. And so there's two slides here. I'm starting with the classical space-time version. Then I'm going to move on to the relativistic space-time version. And then both slides are going to show the same picture involving relative motion. But the two slides have different equations for how we calculate relative velocities. Okay, so let's focus on the picture. In this picture here, in this sketch here, it's quite busy. I've got a few things going on. So the important things is I'm thinking about two reference frames. One reference frame is, here I am in the back of this moving truck. And that's going to be one of the reference frames. It's called the unprimed reference frame. And I've tried to draw that reference frame with these green axes here, this spatial axis and this time axis. So that's one reference frame, the moving truck reference frame. And then there's the second reference frame here. That reference frame is stationary with respect to the ground. It's the pedestrian reference frame. And I tried to draw that reference frame. I called it the prime reference frame. And X prime is the position coordinate and T prime is the time coordinate. So the first thing is we've got two reference frames and they're moving with respect to one another. So here's the, it's really confusing for me because everything's reversed. So let's imagine that this is the pedestrian reference frame and this is the truck passenger reference frame. And so we're kind of watching this as the truck passes by the pedestrian. Now, there's one more ingredient. This bird is flying through the air. And the passenger on the truck views the bird, and the pedestrian on the pavement views the bird. And the passenger on the truck views the bird traveling from left to right with this speed here, Vx, unprimed, because that's in the unprimed passenger reference frame. And the pedestrian on the ground views the bird traveling from left to right with speed Vx prime, because that's the primed pedestrian on the pavement reference frame. And so we're going to look at how those are related. And they are related through the final thing that's plotted on here. This vector here, labeled VR, that's the final ingredient we need. That's the motion of the truck reference frame, passenger reference frame, with respect to the pedestrian pavement reference frame. So the truck reference frame, passenger reference frame is moving left to right with speed VR when measured from the pedestrian or pavement reference frame. We could have also denoted the motion of the pedestrian or pavement reference frame from the perspective of the truck. We could have drawn that too, but I didn't draw it. Okay, so I've introduced all these things. VR is the motion of the passenger reference frame with respect to the pedestrian frame. Vx prime is the motion of the bird in the pedestrian reference frame. And Vx is the motion of the bird in the passenger reference frame. And this is how the three velocities are related to one another. If the passenger on the truck told you that he or she saw the bird traveling with a certain speed, and the pedestrian on the ground knew how fast or slow the truck was traveling, so that would be Vx and VR, the pedestrian on the ground could calculate the speed that they see the bird traveling at, or that relationship between the speed they see the bird traveling at and the passenger in the truck sees the bird moving at. And that's this little relationship here. And really it's nothing other than common sense of relative velocities. And I'll show you that it's common sense of relative velocities when we look at an example. And this is called a Galilean transform of velocity between different frames. I mean, that's a long way of, complicated way of saying what it is. It's just how you transform the speeds of the velocities from one frame of reference to another frame of reference. We've applied it to this bird's speed in the two frames of reference. Okay, so that was the first in a pair of slides. Now I'm going to move on to the second of the pair of slides. And that's this figure here. So it almost looks the same. And that's because it is almost the same. I've just changed the Galilean classical transform of velocities into the Lorentz relativistic transform of velocities. So this one now concerns the relativistic velocity transforms, what we call the Lorentz transforms. So again, if you look at the picture, you got two frames of reference. You've got the truck frame of reference, the unprimed frame. You got the pedestrian frame of reference, the prime frame, and you got the bird flying through the air, viewed from both frames, and you've got an indication that if you're in the pedestrian frame, you see the truck moving with some speed VR. If you were in the passenger reference frame, you'd see the pedestrian moving with some speed VR in the opposite directions. So it's the same picture. And again, VR is the relative motion between the two frames, passenger frame relative to pedestrian or pedestrian relative to passenger. And Vx prime and Vx are the velocities of the bird as seen in the primed truck frame and the unprimed truck frame and the primed pedestrian frame. And then finally, I've filled in the equation, analogous equation from the previous side, but now for relativistic space-time, not classical space-time, for how the velocities transform. i.e., if the person in the truck sees the bird traveling at a certain speed, how does the pedestrian on the ground see that bird traveling at, in terms of how fast those two reference frames are traveling with respect to each other? And so here's the equation. Now, the first bit of it looks identical to the Galilean transform, but there's a second extra piece. We divide by this factor here. This factor here is actually just a number, if you think about it. It's 1 plus a velocity times a velocity of a velocity squared. So this is nothing other than a number, but it modifies, alters, changes the transforms of velocities in relativistic space-time. Would I say that, so I'm looking in chat now, would I say that the Lorentz equation is more specific equation than Galilean? What I would say is, let me say a couple of things. At low speeds, meaning speeds much smaller than the speed of light, the Lorentz transform essentially becomes the Galilean transform. So if objects, the bird, are traveling at low speeds, and the relative speeds of the two reference frames are low speeds, much smaller than the speed of light, this piece, this extra piece, becomes 1. And that means that the Galilean transform is really built in the Lorentz transform, in the way that the Lorentz transform behaves at low speeds. But when you go to high speeds, when you've got high speeds compared to the speed of light, high speed for the bird or high speed for the relative motion of truck and pedestrian, then the transforms are different. So the Lorentz one is strictly correct everywhere at all speeds. The Galilean one is just correct at low speeds compared to the speed of light. Okay, so those are the two equations. Now what might help now is to look at some examples. So firstly, I just want to, show you that common sense example of the Galilean transforms. Because I think with numbers, you see just how much common sense the Galilean transform makes. And then with numbers, you see how weird, peculiar the relativistic transform is. I think the numbers really stress that. So this is an example of the Galilean transform. So again, it's the same picture as before. We got two observers, the pedestrian and the passenger, observing a bird flying through the sky. We're told that the truck is traveling at 10 meters per second relative to the pedestrian. So there's these two frames here, passenger frame, pedestrian frame, and the passenger frame is traveling towards the right 10 meters per second through the pedestrian frame, or vice versa, right? The pedestrian frame is traveling at 10 meters per second to the left through the passenger reference frame. So we're told that piece of information. And then we're told that the passenger sees the bird flying at 4 meters per second. We're asked what speed the pedestrian sees the bird flying at. So I've denoted those two things here. In the passenger frame, we're told the bird is observed to fly at 4 meters per second. in the pedestrian frame, we're asked to figure out what speed the bird is observed to fly by the pedestrian. And this is just a simple example of this velocity transform. So Vx prime, that's the speed of the bird in the pedestrian frame. That's the number that we want to figure out. Vx is a number we know. It's the speed of the bird in the passenger frame. It's 4 meters per second. Vr is the relative speed of the two reference frames. That's 10 meters per second. And so all I got to do is plug in the bird speed as measured in the passenger reference frame, the relative speeds of the passenger and pedestrian reference frames, and then do this little calculation, 14 meters per second. And look, just think about how much sense that makes. Imagine first you're in the truck. The bird is getting ahead of you by 4 meters per second. But in the pedestrian reference frame, you see the truck getting ahead of you by 10 meters per second. And so the bird would get ahead of you by 10 meters plus 4 meters per second. And so that's how that velocity transform works. Okay, so there's an interesting question from Jackson, actually. I'm glad you answered. Is the proper velocity the velocity observed by the pedestrian, or is that the wrong way to think about it? That's actually a great question, because it is the wrong way to think about. There's not a proper velocity here. So it's not like the passenger measures the proper velocity. It's not like the pedestrian measures the proper velocity, because in physics, there's no special reference frame. The laws of physics work in all reference frames. So the passenger reference frame and the pedestrian reference frame are both perfectly valid, both entirely valid. And so you can't call one of them proper and one of them not proper. They're both perfectly valid. And this equation is just relating the two. It's showing you how to connect the two. How would you determine, there's another question. How would you determine which reference frame is prime or unprimed? The primes or the unprimes were just a notation that I picked. I could have reversed all the primes and unprimes. If I reverse all the primes and unprimes, so the x prime and the t prime become x and t. The x and the t become x primes and t primes. And the primes in these equations reverse. So the vx becomes vx prime and vx prime becomes vx. So I wouldn't worry. It's a good point. There's nothing special about who I called the prime frame and who I called the unprimed frame. Again, this is just relating the velocities or the speeds seen in those two frames. So I'm not indicating anything special about my choice of who was primed and unprimed. Those are great questions. That's really good. So now let's go to Lorentz velocity transforms. Now, these are the ones that work in relativistic space-time. And now I want to show you how odd things are in relativistic space-time. Okay, so this in some sense is a similar example to the last problem. Last problem, we had two observers watching that little birdie fly from left to right. In this problem, we got two observers watching Dr. Evil fly from left to right. And in the last problem, we were told the speed as seen from one frame of reference and asked to calculate the speed of the birdie as seen from the other frame of reference. And the same question here. We're going to be asked to calculate, knowing the speed of Dr. Evil in Austin Powers' frame of reference, calculate the speed of Dr. Evil in the Earth frame of reference. So let's just read through this question here. Austin Powers travels left to right at 0.7 c, 70% of the speed of light relative to Earth. If Austin Powers sees Dr. Evil flying at 0.5 c, 50% of the speed of light, in his frame, in Austin's frame, what speed do the Earthlings on Earth see Dr. Evil fly at? So it is really just the same as the last problem. The birdie is now Dr. Evil. Austin Powers is now the passenger in the truck. And the Earthlings are now the pedestrian on the pavement. And so I drew a picture, like I drew the last picture, and I denoted it with the speeds that I know. I know the relative motion of the two frames, the Earth frame and Austin Powers frame. I know the speed as measured from Austin Powers frame, and I've got to calculate the speed as measured from the Earth frame. So it's really the same problem. And the only difference is that now with these high speeds compared to the last problem's low speeds, I'm gonna have to do the calculation with Lorentz transform of velocities, not the Galilean transforms of velocities. So I've got this extra piece here. And so let's just fill in the numbers and see how it works out. Then I'll look at the chat question. So Vx, that's the speed that Austin Powers sees Dr. Evil moving at. That was 0.5 c. VR, that's the speed that the Earth moves at with respect to Austin Powers or vice versa. That's 0.7 c. And now we got to divide by this extra piece, which is 1 plus 0.5 c times 0.7 c divided by c squared. So I didn't write out all the c's, this factor here. And this factor here, right, is about 1.35. And if you do the calculation, you get 89% of the speed of light. So the Earthlings see Dr. Evil traveling at 89% of the speed of light. And look, you can see how the speed limit kind of gets enforced here. You can't travel greater than the speed of light in relativistic space-time. In the numerator, if you added the two speeds, you'd get 1.2 c, which would be greater than the speed of light. It's this extra piece that you divide by that stops you, prevents you from getting greater than the speed of light. So that's pretty interesting. If the bird was going slower than the car, so now I've gone crazy. Well, I mean, it might be crazy, but I'm reading the chat. If the bird was going slower than the car, would the passenger of the car perceive the bird to be moving backwards? Yeah, so I would phrase that question in this following way. From the pedestrian reference frame, if the bird was going slower than the car, then the passenger in the car would see the bird as moving backwards. They would have a negative velocity. So we could have done the previous calculation. Instead of the bird having a speed of 4 meters per second from respect to the truck, it could have been minus 4 meters per second, which would mean that the passenger in the truck sees the bird going backwards. And then we would have calculated, I think, 6 meters per second for the speed of bird from the pavement that's seen by the pedestrian. Okay, so there's another great question. How was the second piece of this equation discovered? It was when Einstein developed his theory of relativity based on those two postulates about the laws of physics staying the same in all reference frames, the speed of light being constant in all reference frames. That second postulate about the constancy of the speed of light actually dictates, controls how space and time transform from one frame to another frame, how x and t transform to x prime and t prime. And since velocities are just distances over time, speeds are just distances over time, it really then dictates how speeds transform too. So those transforms that are illustrated by time dilation and length contraction, which tell us how space and time transform, then determine how velocities transform, because velocities are just made from space and time. Okay, I wanted to just show you one more Lorentz transform. And this one's very similar to the prior slide. We got the same two reference frames again. We got Austin Powers reference frame, and we got the Earth reference frame. And they're moving with respect to each other at the same speed, 70% of the speed of light. But now, instead of Austin Powers watching Dr. Evil, Austin Powers is watching the light from this flashlight. And he measures the speed of light from the flashlight to be that speed c, 3 times 78 meters per second. And we want to see what speed the observers on Earth would say that light is traveling with. We're going to do that calculation. So as I say, it's really just the same as the prior problem. It's really just the prior problem with the same speed, relative speed of the two reference frames. But now instead of Dr. Evil traveling at half the speed of light, we've got light traveling at the speed of light as measured by Austin Power. And we want to calculate the speed of light as measured from the Earth. And so we're again just going to use the same equation again. The relativistic velocity transform. So it's the kind of Galilean numerator, Vx plus Vr, divided by this extra piece. So let's go ahead and do that. So in the numerator is the Vx, that's the speed of the light. I actually wrote it here. And there's the relative motion of the two reference frames. That's the 0.7c. So that's the numerator. Numerator is 1.7c. In the denominator, we got 1 plus this product of velocities. Vx is 0.7, sorry, Vx is c, and Vr, the relative motion of the frames, is 0.7c. So I've got 0.7c times 1c divided by c squared. So that's the 0.7 times 1. And you end up with 1.7 over 1.7. Both the observer on Earth and Austin Powers in his spaceship see that light ray traveling at the speed of light. And remember, that was the original starting point of Einstein's relativity, that all observers must see the same speed of a light ray. And so we've sort of come full circle here in this example. We said that Einstein changed how space and time transform between different frames of reference to accommodate the constancy of speed of light. And that change caused the effects of time dilation and length contraction. And then we use those effects of length contraction, time dilation, length contraction. We built that into the velocity transforms, the Lorentz velocity transforms, and we just saw now that it does indeed enforce that the speed of light is seen as the same value in every reference frame. It's always seen at c, the speed of light c. Okay, there's a second question. What would be your approximate cutoff for high speeds to use the Lorentz transform? It's a little hard to just give you a number because it depends how accurate you want to be. So supposing you wanted to know the speed to 1%, well, the cutoff would be higher than if you needed to know it to 0.1% or 0.01%. So I can't give you an approximate cutoff without knowing approximately how accurate you want your result to be. But I can tell you that, even up at everyday velocities, right, which are 1, 10, 100 meters per second, perhaps, you'll never see the effect of time dilation, length contraction, and Lorentz transforms of velocity. You just won't see that effect. Okay, I'm reading one more question. I understand how the C's cancel out on the bottom of the equation, and that's why you haven't included them on this slide. What about the C on top? Well, the C on top stayed there. So there's the C on top. So it's 1 times C. So I kept the C there. And I hope I did that on the last slide too. There is a C on top. The numbers are times C, times the speed of light. Okay, now I want to move on to talking about energy and momentum in relativity. Because we've now explored the important features of space and time in relativity. Let's talk about energy and momentum and laws of motion in relativity. And my next two slides, last night I was sitting at home and I was sitting there on the sofa, and I imagined this conversation between Isaac Newton and Albert Einstein, these two great scientists. And I sort of imagined, well, they're kind of sitting on my sofa, I'm sitting between them. And Isaac Newton says, look, my laws of motion describe how all forces influence the motion of objects. And my laws of motion involve forces transferring energy and momentum, these two abstract quantities. And that energy and momentum overall, though they're moved around, shared around, those quantities are conserved. And now this is where Isaac Newton's really worried about what Albert Einstein has done. Look, you've just changed. This is Isaac saying this. And he's pointing at Einstein. You've just changed the fabric of space-time, this space-time background. Now times aren't absolute anymore. Lengths of things aren't absolute anymore. And there's a speed limit. There's a speed limit that you've imposed on things. So Newton is worried that Albert Einstein's just screwed up the laws of motion and the concepts of energy and momentum by his changes to the space-time fabric. And then here's Einstein's response. So first of all, he admits the truth, right? Yep, in relativity, time intervals are now, not absolute, they're relative. Spatial lengths are now not absolute, they're relative. And I have imposed a speed limit, a maximum speed limit, the speed of light. But although I've changed the space-time fabric, still the concepts of forces transferring energy and momentum, sharing energy and momentum around, and overall energy and momentum being conserved, those concepts are still entirely valid. And so it's reassuring, like a therapist, reassuring Isaac Newton. And all we have to do, he says, is we have to just modify modify a little bit our definitions of energy and momentum. So as we go on to the next slides and we talk about relativistic energy, relativistic momentum, we're going to see how we have to modify energy and momentum in relativistic space-time. And I'm going to start with momentum, and then we're going to do energy. Okay, so in this slide, I'm comparing on the left-hand side classical Newtonian momentum, right-hand side relativistic Einsteinian momentum. And I've written down the equation, classical equation for momentum. Remember, P is the symbol for momentum. And it's just mass times velocity. It's that simple. It's some sort of, I think it was some sort of power of motion. You can get a lot of momentum by having a lot of mass. You can get a lot of momentum by having a lot of speed. So a fast-moving truck has a lot of momentum. A slow-moving fruit fly has very little momentum. Here's the modified relativistic momentum. Momentum P equals mv times the Lorentz factor, this gamma here. So just like that factor controlled time dilation, that factor controlled Lorentz contraction, this factor is controlling, is involved in momentum now. With this modification, so this tiny modification here, right? I just stuck a gamma in there. I just stuck a Lorentz factor in there. I'm pretty sure I could have guessed that myself if I was around at the time with Einstein. With that little change, then all those ideas and concepts of momentum from classical space-time, they're all still true in relativistic space-time. So with this one change, both in classical and relativistic mechanics, we can still think of forces transferring momentum and that overall momentum is conserved. It's also important that in both cases, right, different observers in different reference frames that are moving with respect to one another. If they're looking at, say, supposing you had different observers in different reference frames looking at this picture of these billiard balls. Supposing one of them was just standing at the billiard table with their drink, and another one was cycling through the bar, right? Those are two different reference frames. They're watching at the collisions of these billiard balls. They see the individual momenta of the billiard balls as different in those two reference frames because they see their speeds as different in the two reference frames. But still, they see that momentum is conserved, whether they're just standing there next to the table or they're cycling past the table. They both agree that momentum is conserved in those collisions. And in the classical case or the relativistic case, the equations for momenta are just either mv or gamma mv. The equations for the total momentum that's conserved is the sum of all the mv's of the colliding particles or the sum of the gamma mv's for the colliding particles. And actually, remember gamma. Just think about what it is one more time. It involves the relative motion, v, of the two reference frames. If v is small compared to the speed of light, if v is much smaller than the speed of light, then gamma goes to 1. And that means that this new equation for momentum, relativistic momentum, gamma mv, actually becomes the old equations for momentum when you have low speeds. So the P equals mv is really just a special case, low speed case of the full equation for momentum, P equals gamma mv. I want to, on this graph, just show you how the relativistic and the non-relativistic momentum compare to one another. So if you look at this graph, on the graph there's going to be two curves. Oops. There's going to be a blue curve for classical momentum and a red curve for relativistic momentum. And on the curves are, I'm plotting horizontally, velocity v, this shouldn't be here, velocity v against the momentum. And so I'm imagining starting from, oh, actually it should be there. I want to put it back, but take me half an hour to put it back. Over here on the left of the horizontal axis, that's zero velocity. And over here on the right of the horizontal axis here, that's now the maximum velocity. That's the speed of light. And so this is the allowed range of velocities in relativity. Well, if you plot classical momentum versus v, it's just a straight line here because the momentum is proportional to v. But if you plot relativistic momentum versus v, it's this curved line here because of the gamma factor. It starts out as 1, gamma does, but it ends up becoming infinite when you get close to c, when you get towards c. And so that's why you get this curve for the relativistic momentum, but this straight line for the classical momentum. And so as you increase, just imagine an object. Let's take the fruit fly. Let's grab the fruit fly, and we're going to make the fruit fly travel initially slowly, then we're going to get it up to the speed of light. So as we exert our forces to increase the speed of the fruit fly, we're transferring momentum. And what you see is you can keep transferring momentum and you can go more and more momentum, but no matter, even if you transfer infinite amount of momentum, you can't make the fruit fly go faster than the speed of light. That is, as we increase the speed from 0 to c, gamma, the Lorentz factor, grows from 1 to infinity, and the momentum, the relativistic momentum, grows from 0 to infinity. And so that's all quite interesting. Okay, got a quiz question. Okay, I think the quiz is up. So this says, consider the limits in relativity of speed and momentum. And we've just been talking about that. So we talked at the beginning of class that there is a limit on speed. It's the speed of light. You can't go faster than that. And then we just talked about, in discussing relativistic momentum, that there's no limit on the momentum. You can have infinite momentum. And as you push something faster and faster, what would happen? If you could push something faster and faster, you can give it more and more momentum. You can have its momentum grow and grow and grow and grow and become infinite, but you can't make it go faster than the speed of light. So there is a limit on speed, but there's no limit on momentum. Okay, final topic for today, which is relativistic energy. And this is related to mass. So I've got 3 slides here. I was imagining, as I sometimes do, I was imagining how growing up, going through elementary school and high school and off to college and all that stuff, and how I don't know why I was thinking this, how my understanding of mass changed, how my teachers changed my understanding of mass. So I remember at elementary school, you know, mass, I was taught mass there. Mass was kind of the amount of matter, the quantity of matter. So a mouse would have a small amount of small mass because it's made of a small amount of matter, and an elephant would have large mass because it's made of a large amount of matter. So that was my earliest, that I recall, experience with the concept of mass. I guess at high school, yeah, I mean, I did physics at high school. I learned another way of thinking about mass, and it's kind of the Newtonian way of thinking about mass, and it's through Newton's laws of motion. In Newton's laws of motion, when you exert a force on an object, that object is accelerated by that force, and that acceleration is in inverse proportion to that object's mass or inertia. And so that's another way of thinking about what mass is, not as an amount of substance, but as kind of the amount by which an object, a mouse or an elephant, resists having its motion changed. And then finally, I learned an even deeper understanding of what mass is. And I learned this from, not directly, but from Einstein, that the way we, at the deepest level, the way we should think about, visualize mass is that mass is just a form of energy. Like kinetic energy is a form of energy, moving energy, like thermal energy, or like electrical energy, magnetic energy. So mass is a form of energy. And you can see that from, this is Einstein's famous equation, E equals mc squared. What does that really mean? Everybody knows this equation. My aunts and uncles and cousins and whatever, they all know this equation. But what this equation means to me is it's saying that mass is a form of energy, and the amount of mass, the amount of energy in a certain mass object, supposing you had 1 gram, let's say a certain amount of mass. So supposing you have 1 kilogram, a certain amount of mass. The amount of energy that's equivalent to that mass, that is stored in that form mass, is mc squared. 1 gram times the square of the speed of light, or 1 kilogram times the square of the speed of light. And so that equation to me is saying that energy and mass are equivalent things, that mass is a form of energy, just like motion, moving, kinetic energy is a form of energy. Chemical energy is a form of energy. Mass is a form of energy. Okay, so now I'm going to introduce to you the relativistic equation for energy. So I'm going to try and quantify it a bit more. And you'll see in this relativistic equation for energy, you'll see that E equals mc squared. And this equation for relativistic energy tells you the full story behind that E equals mc squared. So, you know, that E equals mc squared, that's like the catchphrase of relativistic energy. But behind that equals mc squared is this complete story of energy, relativistic energy, and various types of energy. So let's walk our way through this equation. So imagine an object. So we could imagine the mouse, small mass, little m. Could imagine the elephant, big mass, uppercase M. Just imagine some object. And you can imagine that object is in motion. The mouse is in motion, or the elephant is in motion. And we're going to write down what the total energy of that moving mouse, that moving elephant is. And as we write it down, we're going to expose the fact that that moving elephant or that moving mouse has two distinct contributions to its total energy. That familiar kinetic energy associated with the motion that we've met in 211, and then the new piece, the equals mc squared piece, which we're going to call the rest energy. That's even there when the object is not moving. So the total relativistic energy of a moving mouse, elephant, particle, whatever, is E equals gamma mc squared. And again, you see gamma, the Lorentz factor, coming in here. Every time you get a relativistic equation, you're going to get these gammas. That total energy, so this is the total energy of the moving mouse. This is the total energy of the moving elephant or the moving whatever. That total energy, we think of it as having two pieces to it. RE, that's rest energy. So that's a piece that would be owned by the mouse or the elephant, even if it was stationary. And then KE, that's kinetic energy. That's the piece that is associated with the movement, the motion of the mouse or the elephant. And the equations for those two pieces, well, mc squared is the rest energy, and we just met that. And if mc squared is the rest energy, the remainder, the kinetic energy, must be gamma mc squared minus mc squared, because we've already used up the mc squared. It must be this piece here. And so this was Einstein's new kind of picture understanding of energy. When you think about a moving object like a mouse or a moving object like an elephant, then the total energy of that moving mouse or elephant comprises both a rest energy associated with its mass and a kinetic energy associated with its motion. That first piece does not care about the motion. That's the rest energy. That second piece does care about the motion. V is in the gamma. So that does care about the motion. And so that first piece, that's the rest energy, mc squared. That second piece is the kinetic energy, gamma minus 1 mc squared. Now, there is an interesting point. As with all of these relativistic equations, gamma minus 1 mc squared. It's interesting that if you again imagine V over C becoming very small, everyday speeds, this equation here, which contains inside it the velocity v of the moving object, actually does just become 1/2 mv squared. So again, just with the transforms of space and time, just with the transforms of momentum, also with the transform of energy, if you work your way down from high speeds to low speeds to everyday speeds, then all those equations become the familiar equations from classical mechanics. There was a question in chat. It was related to momentum, but let me just answer it. So it asks, an object is moving at the speed of light with fixed mass. Wouldn't it have a fixed momentum? And the answer to that is no. If the correct equation was just mv, then if an object was moving at the speed of light, c, with a fixed mass, m, yeah, it would have a limit. Couldn't be more than mv or mc. But in this case, in relativistic case, the equation is gamma mv for the momentum. And as you make v bigger in gamma mv, not only does v get bigger, but gamma gets infinitely big. And so as you make v close to the speed of light, the momentum becomes infinite. Okay, just to give you an example, I haven't shown you the calculation of this, but I did the calculation of this, and I just wanted you to appreciate this. I thought about that little mouse down here. This guy, I weighed him this morning. He's only 50 grams. And when he ran across my kitchen floor, he was running at 4.5 meters per second. So if you take an object that weighs 50 grams and runs at 4.5 meters per second, you can calculate the kinetic energy that object has, and you can calculate the rest energy that object has. You could calculate them now by kinetic energy is gamma minus 1 times mc squared, and the rest energy is mc squared. Or because the speeds are low, you could actually just use here, you could use the low energy approximation, half mv squared, and then mc squared. If you do that, the kinetic energy, it's really rather puny, it's half a joule. But you discover that the mouse's rest energy, that's actually enormous. It's 5 times 10 to the 15 joules. And it's because you're multiplying that 50 grams by the square of this enormous number, the speed of light. And so if you think about next time the mouse runs across the kitchen floor, well, give the mouse credit. It doesn't have much kinetic energy, but it has a lot, it really has a lot of rest energy because its mass is a form of energy, and that amount of energy is enormous. Okay, so I've got a example problem here involving these different types of energy. So what you're seeing in this picture is a national lab near Chicago. It's called Fermi National Accelerator Lab, Fermi Lab. And at Fermi Lab, they accelerated protons. It's an accelerator lab. They accelerated protons to an energy that corresponds to 400 times their rest energy. Now remember, think of the mouse when you think of that 400 times the rest energy. The mouse had a kinetic energy that was almost nothing compared to its rest energy. At Fermi National Accelerator Lab, the reverse is true. They've accelerated the protons so they have a total energy 400 times their rest energy. So the rest energy is almost nothing compared to their total energy. And we're going to be asked a few questions here about that circumstance. So this is all we're told, right? And then we're going to be asked, what is the rest energy of a proton? We'll figure that out. What is the total energy of these protons? And what is the kinetic energy of these protons? So remember, those are the three types of energy we've been talking about: total energy, rest energy, and kinetic energy. And the total energy is just the sum of the rest energy and the kinetic energy. To help us is this statement here. So this is a statement about the proton's mass. Now, when we talk about elementary particles, like electrons and protons, and we're going to be talking about them over for the rest of the semester, we don't, and you, I'm sure you've done this in chemistry, you wouldn't talk about the rest, generally don't talk about the mass of a proton or electron in kilograms, because it's not a very convenient unit. We more often in physics talk about the mass of a proton in what might seem strange or weird units, but they're very convenient units. We talk about them in electron volts over c squared, or mega electron volts over c squared. Now, it's a mouthful of a unit, I know that. But it is just like a gram or a kilogram. And it's just more convenient than working with grams or kilograms. So on this slide at the bottom, because we haven't used, I don't think we've used electron volts over c squared for units of mass so far, I've just written down the mass of a proton. A proton, each proton has a mass of 938 mega electron volts, 938 times 10 to the 6 electron volts. And so that's, in addition to this statement, that the total energy is 400 times the rest energy, we're also told the mass of a proton. And so now with that information, I'm just going to calculate parts A, B, and C. What is the rest energy? What is the total energy? What is the kinetic energy of our little protons as they buzz around the Fermilab accelerator complex? And so here I am. I'm doing this calculation. So I drew a little picture, and I wrote on the picture what I know from the problem. So here's my picture. Let me just point out, this is the ring that the protons go around. And so that they buzz around this ring here. I'm going to clean it up though now because I can't see all the text. And I know the mass of the proton, 938 MeV over c squared, and I know gamma, 400. We were told how many times bigger the total energy of the proton is compared to the rest energy of the proton. Now, the total energy was gamma mc squared. The rest energy is mc squared. So the total energy is gamma times the rest energy. And so if they told us that the total energy is 400 times the rest energy, the problem has told us gamma. So that's an important thing to recognize. Gamma is 400. So I know both gamma and I know the mass of a proton. Okay, so let's go on ahead and calculate the rest energy. That was part A. And that's my calculation here. The rest energy is mc squared. So the mass is 938 MeV over c squared. I've got to multiply that by c squared. That cancels out the c squareds in the numerator and denominator, and the rest energy is 938 MeV. You see there that using grams, kilograms would have been very awkward for doing this calculation. Using units of mass of MeV over c squared and units of energy of MeV, that's very convenient. So that's why we like that. Total energy. Let's calculate the total energy. Total energy, we said, is gamma times the rest energy, or gamma mc squared. So it's 400 mc squared. And so it's 400 times the rest energy, 938 MeV, and that comes out to be this number here, 375 billion MeV. Is that right? Yeah, 375 billion MeV. 375,000 million MeV. So that's part B. And then part C. Part C asks, what is the kinetic energy? Well, you know, these three types of energy, total energy, rest energy, kinetic energy, are related to one another. The total energy is simply the sum of the rest energy and the kinetic energy. The kinetic energy, therefore, is the difference between the total energy and the rest energy. The total energy is 3.75 times 10 to the 5 MeV. The rest energy is 938 MeV, and if you subtract one from the other, you get 3.74 times 10 to the 5 MeV. And so that's the total, that's the kinetic energy. The proton had a total energy that's 400 times its rest energy. So 399 times the rest energy is the kinetic energy. The remaining 1 times the rest energy is the rest energy. And so that's how energy breaks down for these protons. So say it's the opposite of the mouse. Here, the proton's energy is mostly kinetic energy. You know, it's 399 times as much kinetic energy as it has rest energy. For the mouse, it was the opposite. It was almost entirely rest energy and very little kinetic energy. Okay, I'm going to finish there with a little summary. There is one more example that I've got in my slides if you want to take a look at it. It's another one about rest energy and actually about how we get nuclear power from nuclear fusion. But let me just summarize today's class. We talked about relative velocities. We met equations for relative velocities in classical physics and relativistic physics. And we saw how they produce a maximum speed, a speed limit in relativity. We talked about, in words, you know, the laws of motion and the action of forces, but that really was to lead us on to our discussion of relativistic momentum versus classical momentum and relativistic energy versus classical energy. And so I'll end there.